Hello, in this video we're going to briefly talk about Bayes' theorem. Let's first talk about conditional probabilities. This rectangle over here corresponds to the probability of event A, while this one over here corresponds to the probability of event B. There is also an overlap between the two of them, which corresponds to the probability of event A and B occurring together. This is called the intersection of event A and B. Now, what would be the conditional probability of event A given B? The conditional probability of event A given B means knowing that B is true, what is the probability of observing A? So essentially, this is the same as restricting the parameter space only to B. And in this case, the probability of observing A would be equal to this sample space. So we can write that the conditional probability of A given B would be equal to the intersection for two events as a fraction of the probability of observing B. And what about the probability of observing B given A? In the same manner, this can be seen as restricting the sample space only to A. So this would be now the probability of observing A and B as a fraction of the probability of observing A. These two are equal, so we can write PA given B times the probability of B is equal to PP given A times PA, or that PA given B equals probability of B given A times PA divided by PB. And this is Bayes' theorem. So Bayes' theorem is a very nice way to find the conditional probability when the reverse conditional probability is known. One of the most common applications in clinical practice is when we have a positive test result and we ask ourselves, what is the probability of this result coming from a truly diseased individual? So this is, what is the probability of disease presence when we have a positive test result? And according to Bayes' theorem, this will be equal to divided by the probability of testing positive. Now the probability of testing positive, given that disease is present, is equal to the sensitivity of the test, while the probability of disease is equal to the prevalence of the disease in the population under study. The probability of testing positive is equal to the probability of testing positive when disease is present times the probability of disease presence plus the probability of testing positive falsely when disease is absent times the probability of disease absence. Again, this one here is the sensitivity of the test, this is the prevalence of the disease, this is the false positive fraction, which as we have seen is equal to 1 minus specificity, and this is equal to 1 minus prevalence. So what we call the positive predictive value of the test, or otherwise the probability of disease presence given that the test is positive, is equal to this equation.